without any further delay. So, as Jangisa introduced me, I'm Iqra Altaf. I'm here to present a talk on descriptive statistics in data analytics. All right, so how this is placed exactly with the current FTP, we'll discuss it briefly. So, following is the outline of my talk. It's going to be mainly relying on the mathematical sides of data analytics. Particularly, we are going to discuss two main summarization techniques that we use in data analytics, which is data summarization and graphical summarization. Basically, as you can see from the subtopics, there are a lot of terms which I'm sure most of you have already seen in your education, like whether it's in your college or in your school. But I'll try my best to place it in the context of FTP. All right. So let's start with some motivating example. So most of the times when we talk about data science, the kind of motivating examples are usually from statistics or maybe some financial data. But since we have been in lockdown for so many months and most of us have switched to watching daily soaps on TV or OTTs, which we were not able to do in our daily schedule. So I start with an example of TRP. I'm sure most of you know what an TRP is, and TRP is basically a television rating point, and all these daily soaps are always mastering the people's mind by trying to achieve the top spot in TRP, right? So TRPs are basically a tool which tell you like which programs are most viewed by the people. They basically give a picture of the choice of people, like which channel is more popular. Like in India or like in most of the household, like in our families, our mother, sister, like they are more inclined towards the Star Plus channel. So like how do we say Star Plus is a more popular channel with females? Like all this is based on TRP, right? So like how do we calculate this TRP? Basically for the calculation purpose, some devices are attached to TV sets in some few thousand viewers houses, but this is done across the geographic and demographic sectors. Now you might ask, like, I don't have a device attached to my TV set. So this is done in a sampling manner, okay, and the device is called people's meter. So what it does, it reads the time and program that a viewer watched a particular day for a certain period of time. So basically, it's sort of keeping an eye on what do you watch, which channel do you watch, and how many hours do you watch, right? And similarly, an average is taken of these values for say 30-day period or a 1 week period. In addition to this, maybe those people who with whose TV these devices are attached, a personal interview may also be asked, like, what is your review? What is your strategy? What do you think? How is this program? Do you find this interesting or not? A sort of interview can also be taken to compute or overall characterize this TRP rating. Okay, so essentially what we are doing is we are dealing with data, right? Data to for TRP estimation, right? So again, we are going to get loads and loads of data from the TV sets of different people, and eventually what we get is a data set. Okay, so this is just a motivating example. Now, before we move on to the exact statistical measures, let's look at some definitions. Okay, so defining data. So I'm sure since it's a workshop on data science, so this term you might have encountered a lot of times already. So just to recapitulate, data is basically a collection of observed values which represents one or more characteristics of some objects or units, right? And coming back to our same motivating example of TRP, so in this case, data collection will consist of different attributes like age, like what is the viewer's age? Are children viewing? Are adults viewing it? Are young adults viewing it? Or are senior citizens viewing it? So that's one attribute. Similarly, the sex or gender, like are the males watching it or female? And then happy is generally things which you get from the interview of those people, like are you too happy about this watching this program, or you're very happy, or you're not happy but you're just watching it for time pass. Similarly, other attributes, TV hours, how many hours do you really attend this TV program, right? So this is all about data. So if you look at the database of the same example, TRP data set, what it will be look like. So this is just a screenshot of this worksheet. So you can see there are different viewers. That's the first column, and then the four columns are the different attributes that you get from this data set. So now, as you can see, this data set is nothing but a collection of units, right? And each viewer's observation or each viewer's recordings for different attributes is what is an observation for a particular viewer, right? And as we see for a particular viewer, different variables are there, age, sex, happy, TVRs, and for each viewer we'll have corresponding values for these uh, information units, right? So while I'm speaking, I'm talking about two things, data and information, and I'm sure every one of us might be aware like what is the difference between the two, right? So data is more of like you have just heaps and heaps of data which don't make any sense, but once you start processing them, like as you can see in this data screenshot of the web page, that what we have done is we have tried to sort this data into columns. So like when we are getting the data, it's just unprocessed, but once we have put that in a proper sheet with having separate columns for age, sex, happy, TVRs, we are saying that we are trying to extract some information from it, right? So what is information actually? It's nothing but like when you process data so that you get some inferences out of it, right? So this is data. Now, what is population, right? Population is basically a data set representing the entire entities of interest. That is, coming back to the TRP example, what is our population in case of TRP data set? So all the TV viewers in a country or a world is actually our population, right? But one point to note is that all people in the country cannot be our population. Why? This is a very critical point, because if we are doing survey A, which is now you want to calculate TRPs. So our interested targeted audience is something different. We are interested in TV viewers. So why should we survey also those who don't actually watch TV, right? So basically, population in statistical learning is actually a way to identify your audience, right? So suppose I was doing a survey, or I was collecting a data set on whether polio has been eradicated in some state or not. Naturally, my population will not be TV viewers, right? My population will be those families who have some younger children, like below 5 years children, so that I know like whether the polio vaccine has been given to them or not. So basically, what I want to say is that when we say a population, it does not mean like entire population of the country or world. What it means is that what is your actual interest? What is the topic of interest? What is your survey all about? Right. So if you know what is your survey, you know what is your population. All right, now moving one step ahead is sample. Now, what is a sample? Sample is basically a data set consisting of population, or you can say it's a subset of population. Okay, so normally sample is something which represents your population. It's something like if you talk in current day context, if you see COVID vaccines, everyone is in the race of developing the first COVID vaccine. Like, how do they test? They're not going to give this vaccine on trial basis to the entire population. But how they do it? They give it to some sample and then they take the inferences out of it, right? So sample is just a subset, but it should be, the critical point is it should be representative of the population. That means it should cover all the aspects of population. Okay, so again, to make you understand properly, so if we consider back the example of TRP rating, so we know what is a population, it's all the TV viewers. Now, how do we say a sample is a proper representative of this population? It's only possible then when what we take in sample is people from different age groups, so that we have complete picture of the entire population. It's not that suppose what we do, we take a sample wherein we only take females and maybe only between 30 to 40 years old, okay, and maybe just housewives. So that's not a correct picture of the population. So sample should be something which represents your population as a whole, right? Now coming to the statistics, so like we are trying to build up the terms which are going to be important in this talk. Now, what are statistics? Statistics are basically different kinds of quantities which you calculate from the data that you have collected, right? So like mean, median, mode, all these kinds of statistics, I know you have studied them. That's basically what captures the statistics. Those values which somehow quantify your data or represent different characteristics of your data, right? So we started with data, and now coming to the last definition, which is the statistical inference. Now, what is statistical inference? Statistical inference is the process of using sample statistics to take decisions about the population. Okay, so this is like these definitions also capture like what is going to be the talk about. So we started with the definition of data, and we are ending with the last definition, which is statistical inference. So what we do is whenever we have a data set and we try to analyze it, that's what is the idea of data analytics. What is our end goal? Our end goal is to gather some inference out of it, right? Because if you have a data set, eventually what you want to do is you want to take a decision from that data set, right? Just if we take back the example of TRP data set, So eventually what we want to do at the end is we want to see the inference that, suppose we want to check what is the relationship of the age of viewers with the number of hours they watch. Like if there is someone who is like a young adult who is doing his job, naturally his viewing TV hours will be lesser compared to someone who is always at home, right? So this is the entire picture of the data analytics. That is, you always have a data, and why do you require the data? Eventually you want to gather some inference so that you can take decisions about the corresponding population, right? So all this statistical inference, like how do we do it now? Okay, so you have already, I'm sure in other my other colleagues might have given you already good talks about the different topics, like how, what all models we use, how do we actually do it. Now let's try to see the mathematical part of it, like what kind of measures do we use to actually gather those inference. Okay, so broadly speaking, you can gather the inference or you can summarize your data using two techniques. One is your data summarization, other is the graphical summarization. So we'll start with the first part, data summarization. So as I said, what we try to do in data summarization is to gather an overall picture of the data, right? So like you want to see how does our overall data look, so that, remember, always the end goal is you want to take inference of some inference from that data, right? So to take inference from some data, you need to have the overall picture clear, like how does your data actually look like, right? So also the other use of data summarization is to identify the outliers. Outliers mean something which is not fitting in your data and which can cause trouble if you want to find a model which fits you most, or anything you want to do in data analytics. These outliers are always problematic because they are something which is not fitting in your proper model, which is something which is not matching what is your requirement, right? So data summarization techniques that we are going to discuss are broadly divided into two categories, measures of location and measures of dispersion. And I'm sure most of these techniques you have studied, but let's try to see what else we can gather from it. So coming to the first category, which is measurement of location, or it's also known as measuring the central tendency. Basically, in this, the idea is to summarize the information from a single number. Okay, so you're trying to look at a single number, okay, different sample values, and you try to take inference from that. That's why it's a measure of location. You're talking individually about single numbers. Okay, and most popular measures of location that we have been studying is mean, median, and mode. Right, so there are different techniques by which these four measures of location can be calculated. Broadly, these are of three types: distributive, algebraic, and holistic. Let's see what this means. So distributive measures are those measures which basically can be solved using a divide and conquer technique. Right, so divide and conquer technique means like wherein you can divide your entire data set into smaller subsets, and then you can compute the measure for the small subsets. Okay, so that is divide. You divide your data set into smaller subsets, okay, and then compute the measure for these smaller subsets. Finally, when you have a major value for all the subsets, then you combine the result to get the overall result for the data set. So that's called a distributive measure. Okay, so note that not all measures can be calculated in this manner. However, some examples which can be calculated using this method is sum and count. Because if you see in sum, whether you take sum of 3 and then suppose you have 10 numbers, whether you take sum in 3 3 1 or you take sum in 5 plus 5, overall end result is going to be the same, right? So basically distributive measures are those wherein we can do this divide and conquer technique. Second is algebraic measure. Algebraic measure is wherein you again use distributive measures, like we just saw examples of distributive measures sum and count, but you apply some algebra to it. Like to calculate average, you need to divide sum by count, right? So algebraic measure is wherein you combine different distributive measures using some algebraic techniques, right? Like here we are dividing it. Now coming to the third one, which is slightly different, which is also known as holistic measure. So like if we linguistically see, what does holistic mean? Holistic means the complete picture or whole. That's what these measures also mean. So those measures which can be computed only on the entire data set, right? Not like the distributive measure, which can be done in divide and conquer technique. Those are called holistic measures. Some examples of it is median and mode. So just to recall, we'll be discussing this also again. Mode is the most frequently available value in your data set. Naturally, see, if I'm saying I want to calculate the most frequently occurring value in a data set, naturally I need to have the entire data set in front of me, right? I cannot do, suppose I say that I have 10 numbers, okay, and suppose total I have 100 numbers, okay, but at a time I'm giving you just 10 numbers at a time, right? And I'm telling you which is the most frequently occurring number in the entire data set of 100. You cannot predict the future, like what is going to be in the future, which number is going to be frequently occurring, right? So that is the meaning of holistic measure, wherein you need to have the entire data set so that you can calculate them, right? In mean, this was not an issue because you can have a mean of the 10 values and then add it up to the another 10 values, and so on. You can calculate the running mean. But when you have some measure which requires the entire picture of data set, that is called the holistic measure. Now, if you come to the first simple measure, which is the mean, so there are different kinds of mean which are available or which we are going to use in our data analytics or in general in any statistical technique. Mainly, there are three mean techniques: simple mean, weighted mean, and trimmed mean. So simple mean, as you can simply say, it's a simple arithmetic mean or average, as you can see. So if x1 to xn are different sample values, we are just summing up all the sample values and dividing by the number of samples. So this is a simple mean, right? So it's not any difficult thing. Now, what is the weighted mean? Weighted mean is the simple thing wherein what you have done, in addition to the previous slide, what you are doing is here everyone has a weight of 1. Now, what you are doing, you are adding weight to the sample values. Okay, just to give you an example, it's something like if all the attributes of say a data set, like in TRP data set, suppose you are trying to calculate some a mean of different values, they are all on different scales. So now if you want to give importance to one value over the other, then you use this weighted mean notation, right? So what you have done is to each sample you assign some weight. Okay, so these weights are also important in different machine learning techniques. Like in the neural networks, you try to find weight because again, you don't want to give same weight to all attributes, right? So weighted mean is something which is quite important in data analytics part. Okay, and a simple note is that if you take weighted all weights to be equal, not just necessarily one, just if you even if you take all of them to be say 10, it's again reduces to the simple mean because in the numerator and denominator the constant part will cancel away, right? Now coming to the third and last basic type of mean, which is also very important from data analytics part, because what we do in trimmed mean is basically what you remove is the extreme values or outlier values in the sample, right? So what happens is that suppose you have a data set, okay, and suppose it has values in range from say 10 to 100. Now suddenly suppose the one value turns out to be 200. Now if you calculate the average, that 200 is going to dominate your mean and your statistics are left of no use, right? So in trimmed mean, what you do, you you remove the outliers, okay, and then you calculate simply the mean as you have done already, as I discussed already, either the simple mean or the weighted mean. Okay, so the idea is that you have say a data set. What you do is the outliers, because outliers are always going to be either at the top of the data set range or in the bottom, right? So what you do, you trim it off, you remove the end parts so that your mean actually represents your data. Okay, so I hope the problem is clear, because see, outlier, as I gave just an example, that suppose my values are always between 0 and 100, and suddenly there's a value which has 300. Now if you take the average, this 300 is going to dominate the mean, right? So to avoid this outlier value, just trim it off. Okay, so this is a very important technique when you are actually preparing your data set. You know, when you're doing data cleaning or you are actually preparing the data set in for after data acquisition. Right, now some of the properties of mean which are quite useful when you're doing data cleaning or you're trying to create your data set on your own. So first major property is that if instead of taking samples, you have mean of say m samples, you know, you take it in batches. As I said, mean is one of the distributive measures. So suppose you have again 1,000 sample values, and suppose you take samples of 100 batches, so you can also calculate mean in terms of batch. Okay, so as you can see in the first formula, So suppose you have m batches, so ni represents the number of samples in each batch. So you can easily calculate the mean using this formula. Similarly, the second property is very important in terms when you are running simulations. Like if I'm sure many of you might have encountered this. A lot of times we need to calculate a running average. Running average means that every time a new value is coming, you want to calculate the average. Okay, it's not depending that you wait for some time and then calculate the average. So running average is a measure wherein you keep on getting the values and you try to keep a track of the mean. So you can see you can easily calculate the running average using the modified mean formula. So what you have done is, suppose x bar is your mean of n samples, and now your n plus 1th sample comes. So what you can do, you don't need to recalculate the mean starting from first to nth sample. What you do is you simply take the sample value of the n values, multiply by it by n, and then you divide it by total number of terms after adding the desired value. So these two properties makes things easier, makes life easier, because these are some things we frequently use while preparing our data sets. Okay, in addition there are some other properties. So it's something like, if you have want to now remove a sample. Okay, so it's something like you didn't know there was outlier and suddenly you think that this outlier is causing trouble, you delete it, so you don't have to recompute. So you need to picturize this. So I'm sure all of us have seen this meme, but why I try to present it here, because these are something you need to relate to data analytics, because these properties are very useful in data analytics. Because normally these are the operations we do. Like if you want to remove a sample which is causing us trouble, these are the operations that you can't now suppose you have already run your model, and then suddenly you think one outlier is causing trouble. You're not going to recompute the sample again, because it's going to take your time and resources. So what you can do is you can simply use this property. You just use this formula and you're done with it. You don't have to calculate anything. It's just a mathematical step done, right? Similarly, if you have, this is lemma 3.4 is just a generalization of lemma 3.3, wherein you are trying to remove a batch of m observations. Okay, so similarly it can be done. Now coming to the last two properties, it's something like sometimes what happens is that your values are unnormalized and you want to normalize them just to have a uniform scale. So what you do, you add some constant value to all the data set values. Okay, again, now the question comes, do I need to again compute the mean? No, you don't have to, because as you can see from this first equation, you can simply remove or add that constant depending on what operation you have done. Okay, similarly is the case for multiplication and division. Okay, so just to summarize these 6 properties, what we have seen so far is that whether you add something to your data values or subtract or divide or multiply them by a constant, then your mean is not affected. Okay, and how does it relate to data analytics? That means you don't have to recompute the mean, you just have to make an algebraic step and calculate it, right? So these were the basic properties of means. Yes, any questions?
Yes, ma'am.
Yes.
Whenever we apply, let's say, lemma 3.4 or 3.3,
Yes.
will it generate the exact result or it's just an approximation?
No, it's the exact result completely.
That,
So what if you just put in the formula? If you look at the first formula, x bar is what? It's x1 till xn values divided by n. So when I multiply n by x bar, so what is left on the right hand side? So I don't have annotations, and I'm not sure if Teams allow annotations. I can show you. So let me just say it verbally. So if I have just x bar, so what is it equal to? It's equal to
Ma'am,
x1 till x.
ma'am, I have another question is that sometimes what happens that ma'am, when you are determining the mean values, okay
Yes.
ma'am, what happens that suppose you are calculating the age and you are taking the big sample, so we are surveying the population of the district. So what happens that sometimes what happens that there is we are getting suppose from a district we are taking the one block or one village, we are taking small village,
Okay.
we are surveying
Yes.
the village of the population of the village. So at that
Mm-hmm.
particular case what happens that the approximation is considered, approximation is occurred. So in that particular case what should we do? Because in data analysis we have to round up, or we have to again adopt some method to get the exact point.
See, if I get your question right, first coming to the first question. So first is from this formula, there's no approximation. Absolutely, it's a simple algebra wherein what we have done, this x bar. See what we require when we are say suppose adding one value, right? What we have done is if we calculate say mean of n plus 1 terms, what is it? It is x1 plus x2 and so on till xn plus 1 divided by n plus 1. Now,
Yes,
if you look at x bar, it's what? It's x1 till xn divided by n. So that means x1 plus xn is already embedded in x bar. So when I do n into x bar, what I have done is x1 plus xn is placed there. Do you get the point? That part is clear. Basically,
yes,
if
ma'am.
you
Yes.
right, so this in this equation there is no approximation at all. It's a simple mathematical calculation. Now coming to your second point, that in data analytics we always do approximation. See, if you go back to my initial slides, you can see I talked about sample and population. So whenever we talk
Yes, ma'am.
about sample, that in itself is an approximation, right? Because as I gave you example of COVID vaccine also, like when we are trialing it, it's not an exact value that I'm saying that it's going to work for everyone. I tried it on a sample population, which is in itself an approximation. Do you get that
Yes,
point?
ma'am.
So
Yes,
basically, the
ma'am. Thank you.
approximation comes in the place because this entire data analytics things is based on approximation. Because whenever you're talking about sample, whether it's sample mean, sample median, sample mode, it's always talking about approximate representation of that population, not the entire population.
Yes, ma'am. Yes, ma'am. I got your point. Thank
You
you,
got
ma'am.
it?
Thank
All right, thank you. Regarding the second question, what they asked, like we have this village. So again, village is again an example where you have a small sample, okay, and then you're trying to apply something which applies on the entire population on that sample. So there are going to be approximate errors. Like one village is going to be other different than the second. But that's why if you remember from my population slide, I had told you we take it across the geographic and demographic conditions. See, if you're different, if you're taking population of, if you're taking a survey of say 10 villages, you have to take in sample those villages which are slightly different from each other, so that you get the representation of population properly. I
you.
hope
Yes, yes,
that
ma'am.
answers your question.
Yes, ma'am. Yes, ma'am. Thank you, ma'am.
All right.
Thank you.
Thank you.
I
Thank
got,
you.
I got, you cleared, ma'am. You cleared my
Okay.
point. Yes, ma'am.
Okay. Thank you. I really appreciate. Please keep this talk as interactive because it's more of mathematical things, so it gets boring after some time. So you are free to ask any question at any moment of time. All right, so let's continue. So just to recall what we have done so far is we have talked about mean, wherein we have just simple values. But normally what happens is that we talk about groups of data, right? This table we have seen 10th and 12th class mathematics. But the thing is now, as I said, these are all topics mostly what we have studied. But my aim is in this talk to present it in context of the data analytics. Okay, so this topic is something which more links to the data analytics part because what we are talking here is mean with group data. Now, as we can see, like mostly in our surveys, we have a lot of times we have this kind of data wherein we have groups. Like suppose we have like when you talk about the same TRP example, we'll not never deal with something like someone who views TV for 1 hour or 2 hours. We'll always deal with range like 1 to 2 hours. Even in age groups, we'll not say it for individual age. Like what is the statistic about people who are of age 20? What is the statistic about people who are of age 21? It's not done. What we usually do, we group it, right? We say what is the statistic about people 1 to 18, on the basis of some idea. So what I want to say is this is the more critical thing when we talk about data analytics. The mean or calculating, not just mean, calculating all the measures of location with group data. Okay, so in group data, what we have a class wherein we have say x1, x2, which means the lower range and the upper range, and the other property is frequency. The frequency, how frequent is the sample values in that class, right? Now, whenever we talk about mean, we have studied, I'm sure, in 12th class also, these three methods. Mostly we take three different methods of doing it: direct method, assumed method, and mean method, and step deviation method. I'll not go too much into details because I'm sure these are useful, but I'll try to give the insights where and how these are useful. Okay, so let's quickly have a recap of these techniques. A direct method is simple. In this, what you do is you are again going to calculate the mean, but in addition, what you are going to do, you are going to multiply it with the frequency, because now frequency is equivalent to what we saw in weighted mean, the weights, right? And the xi's are not now the sample values, but they are, as you can see here, they are the average of the upper and lower limit of the class, which is also known as class size. Okay, so you sum up the product of the frequency and xi, which is the class size, divided by sum of all the frequencies. So this is again a form of mean, okay, wherein these weights are representing your frequencies. Now coming to the other method, which is assumed mean method. In assumed mean method, what you do, you assume a mean, say A, okay, and it is usually a value of these class size averages, which is the middlemost one, okay, and then you calculate this value di. What is di? Di is simply the difference of this assumed mean and all the sample values. Now just to give you an idea, like whenever we talk about different methods, there should be some logic behind why we go from direct to assumed mean method, right? Let me come to the third method, and then I'll tell you like why these three different methods. Okay, so once you have this di, which is the difference of ai minus xi, then you can simply compute the assumed mean using assumed mean method using this formula, wherein what you do, the mean is equal to the assumed mean plus the sum of product of the fi into di's. Okay, not the xi but the di, the difference, divided by sum of the frequency. Now coming to the third method, which is the step deviation method. In this, what you do, you're some sort of calculating the fraction of your class size in addition to the assumed mean method. Okay, that is, you calculate this ui, where ui is the di xi minus a divided by h, which is the class size. So you're trying to see what fraction of the size does class size fit into. Okay, so these are three different methods which we have seen in our statistics classes. But now what I want to today tell you here is like, why do we actually have these three methods? I mean, any hindsights, like why these three different methods? Anyone from the audience like can say like why three different methods for doing the same group mean? Anything
Ma'am,
that
step deviation method and assumed method,
yes,
there is no difference what I feel, because if you multiply the h and you are getting the simple, you will get the assumed mean method, because you will eradicate the h, then you will definite u, the value of u, then you will get the assumed mean method. So it is
very
similar to almost.
very
But
very good very good observation, very good observation.
but
But that's what I'm
thing
saying.
is
Yeah.
that, ma'am,
Hmm.
in this particular basic method, if you will go to the assumed mean method, step deviation method, and the direct method, in direct
Yes.
method we are getting the value directly, but here what is the variation also simultaneously we are doing. Both the
Hmm.
simultaneous variation we are doing, as well as we are getting the mean value. But in that particular case, we are not considering any deviation part. We are directly going to the mean, and we are holistic aspect we are considering in the direct mean condition. That is my
Uh,
observation is that.
I Your observation about that assumed mean and step deviation was very good. Like your answer is close, but like there is some resource aspect to it as well. So what basically the difference between these three method is that if you look at the values that you will get in the assumed mean and the step deviation, they're going to be smaller. I don't know if you people can recall the tables of the direct method, step deviation, assumed mean method that we do in our statistic classes. The You can see that we are dividing in by some fraction, right? So naturally the values that you're going to use in direct mean, suppose I am dealing with data set which is dealing with millions of numbers, right? So like my table or like my records in direct mean methods are the values, all the values are in millions, so like there are like 9-10 digit numbers. But once I go to assumed mean, I'm dealing with smaller numbers. Like this is the other thing in addition to variation point, which from resource point of view is very useful. So as soon as you move to these methods, you're dealing the, see, like whenever I talk about the, now somebody might ask like why dealing with high numbers is a problem. See, when you are talking about taking larger numbers and saying like very huge data set numbers, then your resource requirement also speeds up, right? So when your requirement is like when you want to reduce the complexity of the numbers you deal with, that's where actually the step deviation and other assuming methods comes. But now coming practically to the techniques that we use currently in data analytics and all, now there are numerous libraries available in Python, which give you, which in at the back end use some combination of these methods. But at the back end, that's what I said, the basic aim of this talk is like what is going on in the back end. In the back end, based on your requirement, you can choose the function which deals with the numbers, or the range of the numbers is such that it suits one of the three methods. Okay, so that's like the main idea. Okay, now coming to other aspect of it, so like mostly what we have is we have data which is inclusive. That is, inclusive data is something wherein your first the number at which your first group ends, that is the starting number for the other range, right? That's called inclusive classes. Okay, so that's continuous. But a lot of times what we see, we have exclusive classes. Like this is also something which we have done in our statistical classes. Like the best example is what we have here. Like if you have classes like 10 to 19, 20 to 29, so there is some discontinuity, right? So 19 and then again 20. So how do you handle this? Because like for all these mean calculation methods, you require some continuity. So what we normally do in statistics is we subtract the lower limit by zero point 0.5 and add it to the zero point 0.5 to the upper limit. And as you can see, with this change, it becomes inclusive. Okay, and this comes quite handy. And what we are discussing currently, this is all automatically done backend by the different functions available in the various Python libraries, NumPy and all. Okay, now moving a step ahead, it's slightly a different way, although not very relative, because now we have different graphical plots representing this. Sorry. So what we discuss next is a graphical method to find mean, which is also known as ogive. Ogive is basically a cumulative frequency polygon graph. So the name ogive actually comes from the ogival architecture. It was found in medieval history, wherein you have the slightly curves, like a tilted S kind of architecture. So this name comes from that. So ogives are normally of two types: less than ogive and a more than ogive. So less than ogive is when basically what you plot. All right. So ogive, as I said, is a graph of cumulative frequency. So every graph, as we know, has at least two coordinates, x and y, if you talk about two-dimensional plots. So what we have is plot between, on one side you definitely have cumulative frequency, on the other axis you have either the upper class or the lower class. Upper class, lower class means that if I have a group, say 10 to 20, so less than ogive will have always the upper limits of the groups, that is 20, 30, 40. Okay, and more than ogive will have the lower class, the lower end of the groups. Okay, so just to give you an example, here's an example wherein there are marks obtained by 200 students in an examination. Okay, and the minimum and maximum are said to be 410, 479. So let's try to make a first cumulative frequency table. Okay, so marks are given in this range: 410 to 419, 420 to 429, and so on. So the first step is always to do what? You make it the inclusive series. Okay, so you subtract minus 0.5 from the lower limit and add it to the upper limit so that it's continuous. Okay, and the number of students or frequency is already given. Now, what is cumulative frequency? As you can guess from the name itself, so cumulative means you're going to add up, right? So like if the frequency of first class was 14, so cumulative frequency is also 14, but cumulative frequency of second class is 20. So the cumulative or the total frequency so far is 20 plus 14 makes 34. Similarly, for third it is 34 plus 42, 76, and so on and so forth. You add, and your last cumulative frequency is always equal to your number of samples. So if you recall, this table is of 200 students. So always your last class will have your sample value 200. Okay, now let's try to make it less than ogive. So in less than ogive, as I said, you're going to take the upper limit. So like upper limit of this class is 419, 429, 439, and so on. So you say less than 419. So what are the total values you have less than 419? It is 14, right? Now, when I say less than 429.5, right? So somebody may say 20, but as you can see, this is why in this ogive we say cumulative frequency is used. Because if I'm saying less than 429, it means not only 419 to 429.5, but it also means less than it, right? So that's why cumulative comes in the picture, because it adds up everything below 429. Similarly, when I say less than 439, it adds up everything below it, and so on and so forth. So as you can see in the last row, less than 479 includes all 200 things, right? And here you can see the ogive of less than ogive. So this is actually ogival architecture, which gives it its name. Similarly, we can do the more than achieve. In more than achieve, we take the lower limit. So the first row is always the highest frequency, and then you keep on decreasing it. Right? Now, why this is important? Because basically, what does it say first of all? It first of all says that after a particular, like you can see from this diagram, you can see that like if 200 is the total mean, like 65% of people have marks in range of 439 to 449. Now, why is this important? Like you saw the mean from less than ogive and more than ogive. Basically, why it's important is that if you take the combination of these two plots, it's another way to get your actual sample mean. The crossing point of the more than and less than one ogive is what is your actual sample mean. Okay, so this is where it becomes important. Okay, so ogive, why it's useful, because if you don't calculate mean through any other method, you just calculate these. As you can see now, you can say like why this is important, right? We have studied three different methods of mean. Now why this is important? As you can see, while calculating these ogive curves, you did no calculation at all. You just calculated cumulative frequencies, which is again very simple to calculate. Okay, so what I'm trying to say, please make this mindset that all these techniques you have studied, but what you need to do in this talk is connected to data analytics. Think of yourself, you're dealing with millions of numbers. So is calculating sum of millions of numbers easier, or just calculating the frequency, which is going to be less, right? So just by having the two frequency plots, you just were able to calculate the mean. Okay, so this is great, right? Because without any calculations, just using two plots, you were able to calculate something which could have taken you a lot of time, if you're dealing with lots of numbers. Okay, so this is one of the things where ogives are important. Okay, and I'm sure in your data visualization talk, you might have already seen different ways of making these plots, using plotly or matplotlib libraries. So once you have drawn the plot, you just need to see the cross point to get the mean without any calculation, right? So this is quite useful. Let's move forward. Any questions so far? All right, so let's
No,
quickly
ma'am.
move to. All right, great. So let's move to some other measures of mean. Again, we are still stuck on mean because like mean is one of the most frequently used statistics in the data analytics. Okay, so now we move to another categories of mean, but based on some sort of what calculation we are trying to fare. Okay, so there are three basic means: arithmetic mean, geometric mean, and harmonic mean. I'm sure you have come across these terms more than once. But as I said again, why I'm discussing it, I want to tell you where do you use which one. All right. So let's start with have a quick review of the means. So arithmetic mean, uh, just to give you an idea, I've just taken two samples, x1 and x2. So arithmetic mean of x1 and x2 is simply their average divided by their number. Right? What does harmonic mean? Harmonic mean is the reciprocal of the mean of their reciprocals. As you can see, 1 over x1, 1 over x2, okay, divided by 2. So it's the reciprocal of the mean of, so it's the mean of the reciprocal, right? Now geometric mean. Geometric mean is basically the nth root of the product of the n samples. So there are two samples, so you take their product and their square root. If there are three samples, you take their product and cube root. Okay, so it's the nth root of the product of the means. Right now, lot of means, right? Means, arithmetic mean, geometric mean, harmonic mean. Now, like what mean do we use? And like, are they really different? Is there any relationship between them? Okay, so let's answer these questions. So geometric mean, formally it can be defined as follows. So geometric mean of n observations, none of which are zero. Okay, so why none of them should be zero? If one of them is zero, is there any problem? Because in arithmetic mean you can have zero, right?
Multiplication.
Yeah, exactly. So this is a very simple question, but I was just checking if people are active or not. So basically, since we are taking a product, so anyone giving zero means your mean is zero. In arithmetic mean, you take a sum, so there's not a problem. But in geometric mean, you need to have all non-zero, right? So you can see from the definition that geometric mean is simply, so this sigma, long sigma means a product, right? So summation is this sigma, and your long sigma, like a pi, is the product. So what you're doing is you're taking the product of n values and they taking the nth root of it, right? Now let's see, is it really something different, or it's arithmetic mean in some disguise, some dressed up arithmetic mean? So actually the fact is that it's not anything different. Okay, let's see how this is exactly an arithmetic mean only. So what we say is arithmetic mean, geometric mean is an arithmetic mean in log space. Okay, so now how do we do it? Okay, so what you do is you take log on both sides of this equation. Okay, the geometric mean equation. Okay, so if you take log on both sides, so from this you get log of x bar, and here you get log of m to the power something n. So if you remember from basic logarithmic lectures, log of m to the power n is n log m. So that means 1 over n comes down, and you have log of xi. And if you remember another log formula, that is log of product of xi is sum of log xi, right? So that means if you now look at this, what is it? It's actually arithmetic mean only, right? Because 1 over n means you're taking average, and you're taking average of what? You're taking average of the logarithmic of the sample values. Okay, so that's why geometric mean is not nothing different, but it's arithmetic mean, but we are dealing in log space, logarithmic space, where your growth is slow. I hope that is clear, like how geometric mean is nothing but a dressed up way of representing the arithmetic mean in the log space, right? Now moving on to the next, which is our harmonic mean. So harmonic mean for the ungrouped data is simply, as I said, it is first the reciprocal of samples and then the reciprocal of the mean, because remember mean was sum of xi by n. So now what you have, n over sum, and what is the sum of? It's also of reciprocal of the averages, right? So for group data you have fi's involved, so it should be clear. Now again you can see this is not something different, it's again arithmetic mean, right? If you, instead of taking x size, if you take 1 over x size and take the reciprocal, then that's simply your harmonic mean. Okay, there's nothing new there. Now the question is like, again the important question, how are the different means useful? When do we use it? Because now if you have now collection of 3 tools with you, arithmetic mean, harmonic mean, geometric mean, where do you use it, right? So there's no such generalization rule, but there is a rule of thumb. Okay, so let's see like what is the rule of thumb, like where should you use what? So for this you have to consider 2 things. Whenever you talk about group data, you have 2 things. One is your observation and another is your range. Range means what is the value that you look at, and observation means what is the exact value of that, right? Just to give you an example of rainfall data. So suppose what is the rainfall is R1, R2, Rn, and for how many days you observed it, that's D1, D2, Dn, right? So rainfall is an observation and day is the range. So you are trying to calculate the rate of rainfall. Now let's try to see. Now there are one instances what you have is your range remains same, okay, but your observation varies. That is, suppose what you are doing is you're trying to find amount of rainfall per week. So that's why your range is 777, right? You have measured the rainfall for 7 days. So your range is same, observations are different. So this is case 1. Case 2 is where the ranges are different, but observations are same. That is, what you are saying is same amount of rainfall, how many days does it take to fall? Okay, this is very useful when you are trying to see the dry period of a particular state. Like suppose you want to see total 50 mm, how many days does it take to take? Like if you are talking about June, July month, the days could be like even like 30, 40, 60 days. But if you talk about the monsoon season, this 50 mm would take just 1 day. Okay, so this is one of the way to represent the case 2. Rains are different, observations are same. Third case is where rains are different as well as observations are different. Okay, so suppose amount of rainfall in different number of days. So this is kind of like a very worst case where you have no uniformity. Okay, now let's see the rule of thumb. The rule of thumb says whenever the range remains same, what you do, you use arithmetic mean. Okay, now I told you something that whenever this case 1 range is same, observations are different, you use arithmetic mean. Now, why do you trust it, right? Why is it useful? Like, I said it and you should not follow. Like, you need to understand why is it useful. To understand this analogy, I want to give you an analogy of distance, speed, and time. So as we know, distance is equal to velocity into time, right? Now, suppose I'm trying to calculate the average velocities, okay, across the different period of time. Okay, I'm repeating what I'm considering the example. I'm so sorry, there is no whiteboard option in this, so I would have written it. Anyway, so what I'm again telling you the example is distance. So distance is equal to velocity into time. And my target is what? I want to calculate the mean velocity. Now consider the first case wherein the distance is constant and time is varying. Okay, so what I'm saying is one variable is constant, distance, and the variable, uh, or rather the other way around. Suppose what I say is time is constant and distance is varying. So what I'm saying is, say, tell me in 1 hour how many distance you are covering. Okay, so the, or maybe 2 hours. So suppose what I say, the table is distance in meters divide, and the second row is time, and time is always 2 hours, 2 hours, 2 hours, 2 hours. So range is same, observation, distance traveled is different. Now as you can see, as we know, distance is equal to velocity into time. So velocity, so we have constant time and variable distance, right? But how is distance and so variable is distance, but how is variable and sorry, the velocity and distance related? They are directly related, right? Because distance is equal to velocity into time, so there's a direct relation. So that's why if we take the arithmetic mean, we know what we are doing. We are going to take the sum of velocities. So there's a direct relation. Now come to the second case. Now when the range is different but observation is same, as you can see, 1, 2, number of days are 1, 2, 3, and so on, but the rainfall is 50, 50, 50, 50. Okay, in this case, always use harmonic mean. Okay, now coming back to the distance, velocity, time situation, as you can see, again our target is to calculate average velocity. Okay, but now what I'm saying is, now in this case the distance is constant. Okay, I'm saying how many days I take to travel, say 100 meter, 100 meter, 100 meter. Okay, so time is varying. Sometime I take 100 meter may take 20 minutes, sometime 30 minutes, and so on. Now in this case, if you see the relation, so what is the variable parameter here? Time. Now if you see, how is time related to velocity? We know time is equal to distance by velocity. That is, there's an inverse relation. That is, velocity is in the denominator. That is why here harmonic mean will be useful. Okay, I showed you in context of distance, velocity, time example, but this applies everywhere. Whenever your range is different but observation is same, then harmonic mean is applied. Okay, and when the ranges are different as well as values are different, in that case geometric mean is applied. Okay, so is it clear to everyone? Let me just go through this last slide, then I'll take
Yes,
questions.
ma'am. Yes, ma'am. Clear, ma'am.
Okay, great. So distance, velocity, time should be very useful in understanding why rules of thumb are very useful. Okay, to just recap the transformations. Now, how all these means are actually the different forms of arithmetic mean. Let's see. So if you have arithmetic mean, so directly you are x bar or x mean is equal to y mean. Now, important case is geometric mean. Now, if you want to change, calculate geometric mean, okay, what you have to do, you don't have to calculate xi's. You have to first bring xi's into log space. That is, yi is equal to log of xi, and then simply take the arithmetic mean of all. And to cancel out the logarithmic effect, you take the exponential. Similarly, how do you do the transformation for harmonic mean? Instead of xi, you take yi's, okay, and then calculate the normal mean and then take its reciprocal. So this is the how arithmetic mean can actually be used to calculate all other means. Okay, and we also discussed which situations, in which situations we should use which mean, right? When your ranges are different and observations are same, which mean should you use? When your observations are different, ranges are same, what should you use? When both are different, what should you use? Right now, just a quick recap of how they are related. Normally, arithmetic mean is less than geometric mean. Arithmetic mean is greater than geometric mean, which is greater than harmonic mean. This is just to give you a picture. Now, coming to other samples. So I'm already running out of time. So let's quickly see. So median is what is the middlemost value, right, in the sample. If n is odd, it's simply the n plus 1th by 2 term. And if it's n is even, so you have this formula. This is the formulas that you have normally. And if you have the group data, in that case, what you do, the first step is to identify a median class. So now how do you identify a median class? For this, you again create a cumulative frequency table. Okay, if you recall, cumulative frequency is what? It's simply the addition of frequencies till that point, right? So you choose a class as median class if its cumulative frequency is greater than n by 2, where n is the total number of samples. Okay, once you have identified that class, then you simply using this formula, you can calculate the median. Okay, where this L is the lower limit of that median class, H is the width of the median class, okay, the class size, and n by 2, as I said, is the number of samples and cumulative frequency of that class. Okay, so this was median. Now coming to the third parameter, which is mode. Mode is basically most frequently occurring value or observation. So as you can see in this case, number 2 is occurring most times, 4 times, so it's the mode. So in a simple observation value, it's easy to calculate, but how do you calculate in group data? For this, you have to identify a modal class. Okay, so what is a modal class? It's different from median class. In median class, if you remember, it was that class whose cumulative frequency is greater than n by 2. Whereas modal class, we don't deal with the cumulative frequency, because remember, what is mode? Mode is actually calculating the most frequent data. So cumulative frequency will not help. Okay, this is logically, you should understand it. But what actually happens is that that class which has the highest frequency becomes the modal class. Now one might ask, like, if you already know the highest frequency class, that should be in the mode, but that is the modal class. Now you need to find the value which is the most frequently occurring. Okay, so that you can do using this formula. Okay, so I'm skipping this formula. It's very simple to go through. Now, the relation between mean, median, and mode, and why they are important. Okay, so to understand this, basically any data set, once you, what is important about a data set is its distribution. A lot of data sets have a very good distribution, you know, well-defined distribution, like normal distribution, or you have a uniform distribution, or maybe Gaussian, geometric, exponential. There are lots of distributions. Right, but normally, how do you categorize data on looking at the data using these 3 parameters? Is you say whether a data is symmetric data, whether it's a skewed, positively skewed, or negatively skewed data. Okay, so how do you visualize it? For this, let's take an example where we have, say, m objects, and their values from v1 to vk. Okay, and you can define the frequency. How do you define the frequency? It's like the probability, number of objects with that value divided by the total value. Right, now for symmetric data, what we have is the mean, median, and mode all are at same point. Okay, so that is your symmetric data. That's typically what most people love to have data, because you have, if all your mean, median, mode are same value, then your statistics are just dependent on one value. So this is something which data analytics love to have, the best kind of distribution that you have. But you can also have skewed data, either positive or negative. In positively skewed data, you can see that mean is greater than mode and median lies in between. In negative, the vice versa happens. Mode occurs at a value greater than the median, right? Now, why these distributions are important? As I said, when you talk about distribution, then you get an idea of what model fits your data, right? And there's an empirical relation. I'm sure, like those who have studied statistics in 12th, they have seen it. This is just an empirical relation, okay? No statistical guarantee for it. Now, coming to the last measure of location, which is mid-range. In mid-range, what you do, you take the average of the largest and smallest values in the set. Okay, in general, how you do it, you take a p percentage, okay, which can be from 0 to 100, and then you take p by 2 of that percentage, and the top and bottom of that percentage you throw out. Okay, and then remaining part you calculate the mean. That is called the mid range. Just to give you an example, if you look at median, in median, what do? Median is the middlemost value. Okay, so it can be seen as a special case of mid-range, wherein you take p as 100. So now if p is 100, so what I said in step 2, you remove the top and bottom of p by 2, yani that means 50%, right? So you remove the top 50% and the middle 50%. So what is left in between is your median, right? This happens in odd, like even you have to take the average. Similarly, if you look at traditional mean, what does it mean? Traditional mean, you don't throw away anything, right? So that's why p is 0. Right, so you don't throw away everything, you take the usual mean. So mid-range is basically a special case of trimmed mean, wherein you throw away some part of data at the top and bottom. Okay, and this is very critical for data analytics, because this is which is used for outlier removal. Okay, now coming quickly to the measures of dispersion. Now, so far what we saw is measures of location. Measures of location means you were treating the individual numbers, right? Now, what we are trying to see, measure of dispersion. Now, how variable is your data, right? That's what we are trying to see. Now, like so far we saw like what is the mean, what is the most frequently occurring, what is the most middle level value, but like how do you overall picturize the data? Okay, let's see that now. So for that, different measures are range, variance, standard deviation, mean absolute deviation, absolute average deviation, and interquartile range. Let's quickly go through them. Uh, so like just to give a motivating example why measures of dispersion is important. So I take two sample companies, company A and company B, who are making fruit juice bottles, and the amount of juice they put in bottle is given in the tables. Okay, so sample A, as you can see, is a lot more uniform. You know, they are close to one. But as you can see, sample B a lot of time drops to 0.8. They're not very efficient. So this means this gives you the variability in the data. Okay, so that's the value, that's the usage of measures of dispersion. It tells you about how variable your data actually looks like, right? So naturally, if you have these tables in front of you, you as a user, who will you be more confident to buy the juice from, A or B? Naturally A, right? Because that seems to be more efficient. B seems to be cheating on you, right? So this is like variability on the data. Now let's quickly start with the measures of location. Uh, Dispersion. So first is the range. Range, as the name suggests, it's simply the range of the values. That is the maximum minus the minimum. Okay, so range actually defines how spread is your data. Okay, sometimes what happens is that you can have a range which is very small, like I am dealing with points, point 0.1 to point 0.9, so that's just my range. So how spread your data is, that is defined by range. It does not tell anything much about the data itself, but it's actually used with other parameters. Okay, so range is simply telling you how spread your data is. Okay, but it does not give the exact picture. Like if I'm saying like I have values from 0 to 100, it does not say me like what is the distribution of the values, right? It could happen that maybe I have just one value from 0 to 90 and all other values are from 99 to 100. Okay, so distribution is not known by range, it just tells you the spread. Now coming to variance and standard deviation, these are more useful in this term. So when you talk about the variance, it's calculated as follows. It's some form of mean, but wherein what you do, you subtract the actual mean from your sample values and take its square, right? So standard deviation, as we know, is the square root of variance. So this basically captures how varied you are from mean. Okay, so this formula we have seen a lot of times in our uh, classes, mathematical classes. But let's try to just picturize, like what does it mean? You are taking, since 1 over n minus 1, it simply means you are taking an average, right? But the question is, what are we doing in the sum? Let's see. In sum, what we are doing is we are subtracting each sample value from the mean, right? Which means what? You're trying to see how different your each sample value is from the mean. So that's how you are actually seeing how much variability is in your material. Okay, so this difference, like it's normal algebra, but we need to connect it to our data set. What are we actually trying to see? We are trying to see here how different we are, how different the values are from our mean, right? So that means we are trying to picturize the variability in our data, right? Now coming to a coefficient variation. Coefficient variation is a simple measure which is calculated by taking the ratio of your standard deviation by mean. So it actually gives the idea of the ratio spread of your data. Not that frequently used in techniques, but definitely it's worth mentioning here. Now coming to other measures, mean absolute deviation and the absolute average deviation. Now, as I said, like whenever we talk about types, I mean, we should never say what are these types. We should always give a motivation, like why do we actually move to these types? Because if we have something like variance and standard deviation, if they are quite useful, why do we move to these steps? Okay, so what is the motivation behind using these two deviations? Basically, what happens again, the problem of outliers rise here. So now suppose your mean has been somehow distorted by an outlier, and so far when you calculated the mean, you didn't know there was an outlier. So we already know mean can very much destructively be affected by an outlier. Okay, remember the example I gave you. Like suppose I have values from 0 to 100 and suddenly I have a value 500 which is an outlier. My mean will be very much tilted towards 500, which is not the correct idea, right? Because my all values are concentrated between 0 and 100. So mean can clearly be distorted by an outlier, right? And if you remember, variance in itself is calculated using the mean because it's different from the mean. So naturally, if mean is wrong, variance is also going to be wrong. So to avoid these effect of outliers, okay, so when I say the avoid effect of outliers, which means your antennas on your head should get alert, because outlier is something which a data analytic people face a lot, because in data sets you are bound to face these outliers. So that means whenever we have outliers, these measures are not going to work, so we need some alternatives. Okay, so the alternatives are the following. One is the mean absolute deviation and other is absolute average deviation. In mean absolute deviation, what you do, you calculate the absolute difference of the sample values with their mean. Now one might ask question like, again I'm using a mean. Obviously you cannot get rid of mean because mean gives the overall picture of your data. But now as you can see in the first equation, you are taking the median of all these values. So if you only take mean variance, you're not taking the absolute value now, but here you're taking samples along with your mean, okay, and then taking its median. So that means the effect of outlier is going to be reduced, reduced, and reduced because there are different measures you're applying to it. Similarly, in absolute average deviation, what you have done, you are again taking the absolute values, but in addition, you are also taking their average. Okay, so naturally, what happens is that by applying different distributive measures, the effect of outliers gets eventually reduced. Right. Now coming to the last measure of dispersion, which is interquartile range, very important. As we'll see in the last few slides, it's very important from the representation point of view as well. So in the mean absolute deviation or the absolute average deviation, we saw they are very robust. Similarly, interquartile range is also very robust. Okay. Now let's see how do we calculate it. In interquartile range, what you do, you first define a percentile or what we say a quartile. Okay. Just to see how we calculate it. In this, what you do, you choose a number p between 0 to 100, okay, and you call that as the pth percentile. Okay, suppose that number is xp. Okay, just to repeat, as I said, this is very important. So what I'm saying is I choose a number p, okay, between 0 and 100. So now suppose that number is x subscript p. Okay, so suppose it's 80. So what does that 80 value mean? 80 we say is the pth percentile, okay, which means that p% of observed values of x are less than xp. Just to give you an example, suppose I have numbers from 0 to 100 and I want to calculate the 50th percentile, which means p is 50. So now suppose my 50th percentile number comes out to be 65. So what it means is that there are 50% of values in my sample which are less than 65. Okay, 50% of all values in general are less than x50. Okay, and as you can see, if I'm saying 50% of my values are less than it, naturally that means 50% are more than it. What is that value? That is median. So 50th percentile is always the median value. Similarly, when you talk about quartiles, quart means 4 parts, right? So in quartiles, we take the common quartiles that we use are 3, Q1, which is 25th percentile, which means 25% of values will be less than it, right? Then second quartile is 50 percentile, which is the median that we know, and third quartile is 75%, right? Which means actually 75% of values are lower than it, right? So now what is interquartile range? Interquartile range is actually Q3 minus Q1. Okay, what are the values? Now we try to picturize it. Okay, you take a range from 0 to 100. Q1 is the values which are in the first 25%, okay, and Q3 are what, which are in the first 75%. Now when I say Q3 minus Q1, what I am getting? Okay, can anyone tell me like what percentage I am getting when I do QR minus Q1? I understand it has been like about 1.5 hours, but I'm just close to my last slides. Anyone can guess like what does, see, we always learn formulas, but what we should try to see is logically what does it say. So try to picturize. So Q3 is all numbers which are like 75% or less, right? 75 is the one bar, and Q1 is 25 or less. So what range I am talking about when I say the interquartile range is Q3 minus Q1?
25 to 75.
Exactly. Right? You are talking about the mid half of the data, that is 25 to 50. So that is what is your interquartile range. What is the dispersion of the median, right? So naturally, median will also fall in this. Very good. So let's see, like, why is now this IQR important? Okay. Again, whenever you see outlier word, you should get alert. So basically, IQR also helps us to detect outliers. Okay, and a common rule of thumb is if you want to detect outliers, you should always take a value 1.5 times your IQR. IQR, remember, is the interquartile range, above and below Q3. Okay, that is usually the range of your outliers. Now, somebody might ask why this formula. These have been tested by mathematicians and statisticians that these are where the outliers range. Okay. uh, Now coming to the important part, which is also related to our graphical summarization, like what is the application of this IQR? Now this IQR is actually important because it helps you to give a very important, useful graphical summarization of data. I'm not sure if you have studied box plots, or I'm sure you might have at least seen it. Because whenever we talk about data analytics, we talk about these models, classification models like KNN, Bayesian classifier, and all. We talk about the accuracy of these values. Okay, in them we use something called a box plot, which we'll shortly see. In that we actually use somehow IQR. Okay, so now let's see what is the application of IQR. We talk about an application of IQL wherein we use a 5-number summary. And what is this 5 numbers? The 5 numbers are as follows. First is the smallest observation in your sample. Second is your largest observation in the sample. Third is your first quartile. Fourth is your second quartile, which is the median. And fourth is your third quartile, which is Q3. Okay, so you have minimum value, minimum most value. Then you have Q1, 25%, median, 50%, Q3, which is 75%, and the maximum. So this is the 5-number summary. Okay, now let's see how does it come. So this is the graphical summarization I was talking about. I'm sure you might have seen this model, not such a big box, but naturally I'll come to one of the sample plots. So this box plot is used a lot in data analytic models, like in KNN, accurate, when you want to compare, like if you're doing some classification on some data set and you have tried a lot of models like KNN, Bayesian classifier, or SVM, okay, and you want to compare the accuracy of the methods. Normally, this is the plot that you might have seen. Okay, so this is known as box plot. And now let's see how this 5-number summary helps here. So whenever you see the box plot, the minimum most line that you see in this, this injection kind of box, like, so this minimum most line that you see is what represents the minimum most value of a number. So this is the first number that I'm talking about. Okay, then the lowest part of the rectangle box is known as Q1, the 25%. Okay, so that means this range is your 25% range. Okay, this is Q1. Then the line that you see in this box, this always represents the median. Okay, and the topmost part of the box represents Q3, the 75% quartile, and the last line represents the maximum value. Okay, so this is how you interpret the box plot. I'm sure you have seen it, but now I hope that you all will be able to interpret it better. Okay, in addition, something is missing here. Normally you also have some circles here. So whenever you see those circles, they are the outliers. And remember, where will they be placed? If you remember, they will always be 1.5 into IQR above Q3 or below Q1. Okay, so somewhere like here and here. Okay, is box plot clear to everyone? Okay, let's see if it's
Yes.
clear. So I've given a sample wherein it's from some paper who have actually run the classification problem, and they've tried different algorithms. Okay, so something which you might be familiar, like it's like naive Bayes, KNN, SVM. Okay, now so these circles that you see, these are the outliers. Okay, so outlier range. So these are below the minimum 1.5 into IQR of Q1 and the QR. Okay, so can just to have an idea whether you understood or not, can anyone tell me what is the median for naive Bayesian classifier from the diagram? Median.
Above the 0.60.
Yeah, exactly. Very good. And can you tell me what is the maximum value for SVM?
0.72.
Yes, so I hope you understood the points, right? So the topmost line is the maximum, the lowermost is the minimum. The first line after this line is the Q1, median, and then Q3. right? So I so I'll stop there. So majority of these slides are basically taken from a talk from Dr. Sebasi Samanta from IIT Kharagpur, and this is the textual reference that I've used. So any questions?